Hey y'all, Evan here, and today we'll be recording our last session for we have two sessions, but our first part of our last homework for separations. Okay. Today we'll be deriving part A. I mean, we'll be doing part A, and then we'll do the mesh, which is just Newton-Ransom's equation. Um, and then we'll be doing Newton-Ransome equation, deriving it, coding it out using only for a single equation, and then for a nonlinear equation as well. And then we'll incorporate is it the Thomas algorithm as well for tridiagonal metric matrices, and then incorporating that in the code as well. Okay, so we're doing the Newton-Ransome and the Thomas algorithm today for part A. And then for part B, we'll be deriving the mesh equation and then implementing it into code and doing the prompts that it asks us to for part B. Okay, so but today we'll do part A. Um, and yeah, so for the first part, we will derive the Newton-Ransome root finder method. So let's start. We will switch over here to the iPad today. I don't think we'll do um, any part in the library. So we will do only iPad. I know my handwriting is way worse on iPad, but it'll be okay. It will be okay. We will get through it together. All right. Let me share screen now. Oh, I forgot to have. Okay. Um, okay, there we go. Share screen, servers. Okay. So, all right. So, what is a new ransom method? So, basically, kind of like what I just kind of said in the prompt, it's a root solver. So it's basically it's another root solver. We have, but how this works is, I'll draw this out. So basically, we have a diagram, and this diagram has a slope function. Okay. Okay. Let me just extend this a little bit. How's this root function? Okay. We know at each function, I mean, each point at the slope where it touches the x-intercept, that'll be our root for the function. Okay. All right. So basically how this works, is that if how this works is, when we do our root solvers that we just implement a random guess. So if we, do a random guess here, we say our guess is up here. Okay. So this is our, initial guess. Okay. How this will work is that our initial guess will kind of create its own slope. I'll do this. Kind of have its own slope where it will have an approximate root. We'll have an approximate root, and from this root, we will have, you know, we will determine where it fits on the actual function slope. So we'll say here, this would be our x1. And from our approximation root that we have from our initial guess, this will just keep on, shooting out roots for us. So our next line from our approximation line from a function, we will then draw another slope, another line. Okay. Okay. So we have a root here, and then we go down as well again. And then we keep doing this on and on again until we actually find the root for the actual function. So this will keep iterating over and over again. So from our initial guess, so instead of like our usual root solvers where we have to keep shooting out new guesses each and every time, we only have to shoot out one guess. And then from our guess, we would just it would keep iterating new and new possibilities for our slope until it actually reaches the actual root for the function. Okay. So that's the main thing. We only had to shoot out. That's the main thing we are using new Ramson method. Due to the fact that we only need to use one initial guess compared to multiple initial guesses for our root solvers. Okay. And how does this work? So we do the derivation now. I'll stick with I'll stick with blue. Okay. We will have so we'll go something like our function of x1 plus our function prime of x1 times x2 minus x1. Okay. Is equal to 0. Okay. So here's our initial function for our new ransom method. And our goal here is to get x2 by itself. So x2 in this case will be so and if we go back to our diagram, I'll finish it out. So if we, have our root that we found, and then we have our new slope here. This slope here will be our new x2. So our x2 is just the final point. What's the next point from our guess? So we'll say so our first iteration was from our guess to x1. So okay, I'm gonna confuse myself with this. I'm gonna give you something. So our x2 is just our next point from our initial point. Okay, so x1 is our initial point that we have, then x2 is the next next point we obtain. Okay. So what we want to do is kind of isolate the x2. So how we do it, we'll first move this bad boy to the other side. Um so that'll give us f prime of x1 of x2 minus x1 is equal to negative f of x1. Um, Next we'll divide by the f prime of x1. So now will give us now x2 minus x1 is equal to negative f of x1 divided by f prime of x1, and then we'll just move the x1 to the opposite side. And then our final equation will be x2 is equal to x1 minus the function of x1 divided by the function prime of x1. All right. So here is our final equation actually for our numerism equation just for a single function. This doesn't incorporate multiple single. This is just a single function, a linear single function. This does not incorporate a multitude of multifunction, nonlinear functions. It doesn't. That's a whole different equation, which we'll get to later. Okay. This is it. This is actually all we need to first start our derivation. So we can now switch to Python. So let's end sharing screen here. Stop share, and we will go to Python. All right. So we share our screen. I actually have this up right here. So, and this is just our, okay. Let's see, is that the right one? All right. All right. So let me just move it here. Actually, let me just make it to, no, I'll keep it like this. All right. So, um, to start off, this over here. Okay. So for our libraries, we're using import numpy as np, we're using import jax numpy as amp. Then we're using jax as well, so we're importing jax, and then we're doing the jax configuration to update to have higher speeds for our Python code. Okay. So that's all we need for this new ransom method. For the Thomas algorithm to be a little bit more in-depth libraries, but just for a new ransom, we just need these libraries. Okay. So and let me also oh shoot. I'll be right back. I forgot to because you know how I always have to transfer my writing portion into a PDF. I forgot to upload that, so I'll be right back, and so we can actually look at what we're typing out. Okay. Okay, so I have the paper now. It's zoomed in because the next part is actually on here, as you can see, the nonlinear equation using Jacobian. So the second part of part A is actually on the paper as well, but I will just be showing the first part for now. Um, so we have our you remember we have our graph that we just have here. It's still terribly drawn like I have here as well. But that's besides the point. We have our code. We have our function equation. We have our equation. And then we also have a sample equation that we use in class that I'll just be using as well. So this would be our sample, our practice function that we have for using for finding our roots solver basically that we use to find our roots. Okay, so first start with deriving our sample function. So define, and then we'll just do F1 for our function. And for our function, we will need well, of course, what is it? F. Well, isn't he X? X for a position. And then we'll return. So we'll just write this equation out now. So X minus 3 times X plus 2.5 times X minus 5. Okay. So this is our first function we are defining, which is literally just this sample equation. Okay. Next part we have to do is that we will use something. Let me use this equation for our finite differences equation using in a numerical differentiation. And this is for, if we go back here, for our f prime function. As you know, f primes means the derivation of the function of our original function. So it's not just we can't just state f. It's not just a regular function. It's the derivative of our actual function. So we have to actually define that derivative. So put derive, something like that. I probably spelled it wrong, but it's okay. And then for this function, we will just need you will need f, you will need x, and then this h term here, this actually is our dx. So if you look at this graph here, I can zoom in. This h actually represents the change in position. So in the equation, the h represents the change in position from our initial x to our final x. So as you see here, it's x first, and then you have x plus h. So it's a difference from our original x. So it'll be our difference in x, and we're actually stating that this would be 0, but we cannot say that. We can't just say 0 because we need that's be like approximation. Is like it can't just be 0 because it would mess up the graphing. I mean, it would mess up the function. So we would need just like our 1e to the negative 8. Close it is basically 0, but it can't just say 0. We had this in other examples in the previous videos before, but yeah. So we'll return now, and we would just state this function. So it'll be f of x plus dx minus f of x divided by, and I'll put this all together, divided by dx. Okay. So here's our second function to have our f prime defined. And now we just need to write this out. So we have defined our Newton's function, which we will need f, of course. Um, yeah, sorry, I'm lying to the rank. We need f, we need x, we need max iterations, because this will run. This is just how many times this function will loop into finding our root, and we'll state this as 100. And then we'll also have a tolerance. So our tolerance is basically how close to the tolerance can do we want it to be. Like where's our range? So we don't want negative numbers. So our tolerance would be 0. But again, we cannot state 0 because Python is not like the number 0. So we would just stay negative e negative 15. Okay. Let's do 16. Or is it 4? It's 14. Yeah, 14 is fine. That's basically 0, but again, we can't state 0. So that's our tolerance. So once our function gets outside of this tolerance, then we don't need to, we can cut the function off. Okay. So let's start. So we would first do for I in range. So we do it like because we're doing a for loop because we're repeating multiple times. So before our max integers, we would then write our equation. So this will be x2 is equal to x1 minus our f function of x1 divided by of x. And put an equal sign again. Minus our f of x1 function of x1. Let me say x1 here actually. I'm just gonna change our function to x. Oh my gosh, there we go. To x1. So x1 divided by the derivative, which is our f prime of f of x1. Okay. All right. Okay. I think we're good here. Why do we have interesting? I don't know why it's like that. We'll figure that out later. And then we also have to state if let me say if that's the problem. If so we also have to state like I just said, if it reaches like if our function is greater than our tolerance, I mean is less than our tolerance, then we need to cut it off. So if what is it? X2. Oh, and if Newton, no, not if Newton. If oh yeah, NP absolute of our function of x1, oh x2, yeah, is less than less than our tolerance. Break the function. Okay. And then because at that point we know that x1 is equal to x2. And we can state that, and then we can print that off. So then we will then return our we'll return our loop. So we return our iterations. We return, I'm trying to remember, our iterations, our x2, and then we also return our function. So f of x2. And then this should be, let's save this. np dot array. There we go. This should be right. I don't know why. We have red lines. Invalid syntax. Is range and invalid syntax. Oh, for I in range. My bad. That's why I was like, what is happening? Okay, for I in range. Shift enter. It's outside loop. There we go. There we go. All right. I was like, something's wrong here. So I forgot to put the in range. But yeah, so basically we have our newest method. So we're finding x2. So we have I, so it's our repeating integers that we're calculating. So in the range of our max integers, we'll use our function, our equation that we have. And then if the absolute value of our function at x2, so our final position, is less than our tolerance, then we break off the function. Because at that point we know that um, the x1, our x1 is equal to our x2. So our x2 value that we have is equal to the root that we have for our function. And then we can plot that down. And then we also want to, we can print out this as well, so we know how many iterations this goes, our new function goes on for. Okay. Missing, oh, hold on. Oh no, my bad. It's just supposed to be in the bracket. I should have just kept it in the bracket. There. All right. So if we do the new method, we do the Newton's function, and we go for f, and then we do 2.8 as our step, as our first guess. We will get f is not defined. Well, it goes to all 100 times. It's not right. Hmm. Oh, I said this wrong. So it's supposed to be F1. If we, oh no, this is right. So we do our newest method and we define our F1 value and our guess. Arrays take 1 to 2 proportional arguments, but they were not given 3. Okay. It should not be over, it should not go to 100. Because I practice the code, so I know where when it goes to. Um, Interesting. It seems, is our tolerance too high? It just seems like it's repeating, actually. Now it's outside 86. Why is it going so far? It shouldn't go to 3 iterations. It shouldn't be this many iterations. Um, Interesting. Um, Let me check real quick, and I'll be right back. Okay. So actually, it was because of a minor error. It's because where I positioned my x1 is equal to x2. I guess since I put it the first time too far, it was outside the loop. So it was actually outside. It was in the loop of the for loop in the return. So it just kept saying that whatever we got for our first guess, it was just gonna keep saying it's equal to x2. So it just kept repeating, even though it didn't hit the threshold, the tolerance threshold. So it never broke. And then the last time it was inside the break. So yeah, it's because where I position my X1, X2. But if we shift enter now, let me get where we're supposed to get. So as you see here, from the 2.8 is our initial guess. We get our first root approximation root is 2.98, 2.98. Then our second one would be 2.99. And it keeps getting closer and closer to 3 until the third iteration, I mean the fourth iteration, because we go 0, 1, 2, 3. So we went 4 iterations. The fourth iteration, it was lower than our tolerance threshold, so it broke off, the function broke off, and we know that our answer is that the root is 3, and of course, at the function, it will be at 0. And if we can check, it does match up because we know one of our roots in our function is x minus 3, which just means our root is equal to 3. So yeah, it worked. All right. Um, so now we have a equation. We have a Python code for a new root finding method, a new arrangement method for a single equation, variable problem. But now our next goal is to implement the newest method in code for a system of nonlinear equations. So using Jacobian. So we'll basically do this now, but for a multitude of functions. So it'll be a multifunctional system where the functions are not non-linear now because you know it's multifunctional. So we will now derive how we will figure that out as well, and then go into coding that. Okay, so that'll be next. Okay. So move on to the next part. Um, we'll be talking about, like I just mentioned earlier, maybe using. Let me start. Let me start. All right, I'm back. As you see, I got a different position for my camera. But to go back to what we're talking about, with the implementation of the nonlinear equation in the Newton-Rashford equation. Okay, so we'll start with that now. We can derive that out, and we can start. My computer about to die. We should be good. And we can work this out. Okay. So let's derive this. And we have a equation like we did for the first part. We have a example equation that we'll be referencing. And I'll use that to kind of explain our example. So, or if I can, it's right here. Oh my gosh, this thing's been bothering me this whole day. Hold on. Yeah, okay. So this bad boy right here is our example equation. So I'm gonna write this down real quick, because I will not be able to see it when I start writing X1. Oh Lord, handwriting still. Did I get the wrong pen? I did get the wrong pen. I found out there's a stylus, which I may get because this stylus is terrible. Yeah, I'm about to get this. I'll be right back. I can't start with the stylus. Plus, I need computer charger anyways. I'll be right back. Okay, I'm back. I got my stylus that works much better, and I actually just wrote it all down on my iPad, so you guys didn't have to watch me, write this down. But basically, the function we're taking the two functions now. The F1, the first function, equal to x1 plus zero point 0.5 times x1 minus x2 cubed equal to 1, and then function 2 is equal to 0 0.5 x2 minus x1 cubed plus x2 is equal to 0. Okay, so now let's go to my iPad. We can start working this stuff out. Okay, so I'll stop sharing here. Always gotta do this part. Excuse me. Share screen. Start broadcast. Okay. All right. So like I just said, we have our two functions here. Um, and what we kind of want to do is that we want to relate both of these into kind of solve on paper, but into like just one big function as it like we want to kind of represent have these two functions relate to our final equation here that we had up here. So we're trying to relate kind of what we did up here for our single function into our multi-function. Okay. What we first need to do, if you did see that, we want to kind of relate both of these to zero. So we can say that x1 plus 0.5 of x1, x2, oh, x1 minus x2 cubed minus 1, okay, is equal to 0. Of course, it's already at the end, but it's equal to 0. Okay. Let me see if I can move this. This sometimes doesn't work. I started finding that out. Oh, it did. I didn't, bro, are you serious? Wow. Okay. Interesting. I just squeezed that in there. But yeah, it's equal to 0. So now we can relate both of these terms. So for the function, we were actually named, we'll kind of combine these. We're just name both the functions as just big F. Let me work this out. And we want to have a bar. We won't have it as a bar for the vector, but this will be related as for both of our functions. We kind of work through here. And of course, like I said, we want to relate to how we have it up here. Our function will kind of, let me see if I can. There we go. Our function will tie into our first part of x of x, f of x1. So how we'll write it out is that this will be f of xn, and xn represents x1 and x2. Okay. So x1 and x2 that we have. And then for our next part, we want to then have plus, and of course, like our problem statement is asked, we're asked to do this by the Jacobian. So this would be the Jacobian. Oh, I forgot, this would be in a vector form. So it's x and of the vectors of the two functions. But it'd be the Jacobian of n of xn plus 1 minus xn. Okay. And then xn plus 1 is kind of like a xn. It is basically equal to the next point for the vector. So it'll be xn plus 1 of the first position and then xn plus 1 for the second function. Okay. So these are our two these are just two vectors that we're implementing into our function. But this is our function that we can relate to our single term here. And I just want to note that this Jacobian times this xn plus 1 minus xn of the vectors is a matrix multiplication. Okay. Since these are, as you see, a 2 by 1 for both of the xn's and the xn plus 1 vectors. Okay. So what we will be doing is that, again, like we did up here, we want to basically single out our last position. So we want to have our, let's change the color. We want to have our xn plus 1 vector be our isolated variable in this case. Okay. So how we can do this is first, of course, move our f of xn to the opposite side. So this will be our Jacobian of n at xn plus 1 vector minus xn vector is equal to negative of the two vectors, the two um not vectors, functions to the x to xn vector. Okay. We then want to move our Jacobian over to the other side. So what we can do is that we will actually just instead of just dividing, we would do the inverse of the Jacobian to cancel this out. So we'll just multiply this by the inverse Jacobian, which will cancel the left-hand side Jacobian out. So then now will leave us with x of n minus 1 minus x of n. Oh, I don't need the parentheses anymore. Is equal to negative of the Jacobian, inverse Jacobian. Okay. And this is still a matrices multiplication. So at f of x of n. Okay. And the last part, we just move this to the opposite side. So move our xn vector to the opposite side. So that will leave us with x of n plus 1 vector is equal to x of n vector minus the inverse Jacobian n multiplied by our functions at x of n. Okay, so here's our final equation for our multifunctional multifunctional root solver um using a Newton's Rashford method. And yeah, we can now plug this in to Python and just work this out. Okay. So let's actually just do it. All right. Let's go for it. So let's get started. I'll share my other screen on my computer so I can stop sharing screen here. So finally zoom out. There we go. Let's move this. And this part right here, if you're wondering what, oh my gosh, this keeps popping. Can you please go now, please? Thank you. Oh my gosh. Thank you. I'm gonna move this to the top. I'm gonna move this to the top. Okay. Hide this document. Thank you. Okay. That was bothering me this for a long time. But this right here, if you're wondering what this was, this is explaining how the matrix multiplication at the for the Jacobian times are xn plus 1 and our minus our x vector will look like. So here it kind of looks right here. But yeah, here it is. Yeah, here's everything. I want to make sure I was also right, but yeah, I did everything right. All right, so let's start. We'll kind of copy the same way how we did our single. So let's start with the our what is it? Our sample functions, our two sample functions. So we'll define, and we can state this as, want to do capital F? Yeah, let's just do capital F. No, that's gonna be confusing. Let's do F2. I'll do capital F and then 2 for, the two functions together. And of course, is our second Newman's Radford. So, and then again, we have our X, and we will return, I can spell return our first function, which is X1, which is, which is X. I think I should be good. Yeah. X plus, because I think about putting the X1 and X2s now. I think I need to also identify X1 and X2. Um, we'll see though. Of X1. Yeah, I probably do have to find X1 and X2. Yeah, makes sense. So X1, um, 25 times, don't forget that, x1 minus x2 to the cubed root, um, minus 1. Okay, I'll put this in a bracket. And then you have our next function is 0.5 of x2 minus x1 to the cubed root as well, plus x2. Actually, I don't think I need a bracket here. Yeah, I do not need a bracket here. I think we're good. Okay. So here's our first function. Pretty straightforward. Use both our functions together. Shift enter. Float is not callable. Perhaps you need. Make sure we put. I put a comma. Here, y. Put a comma though. Interesting. It says it works though, so I'm gonna hide this for now. Okay. Uh, Next, we want to incorporate our guesses. Since we have two guesses, we have to make this an array. So we'll do x naught is equal to JMP dot array. And in our class, I'm pretty sure we did 0.1 and 0.2, and maybe out of order, but those are the two guesses that we had for the two functions that we have. Shift enter. Um, let's do NP then. It's not defined. Oh, I have to redefine everything. Okay, I was wondering like why is it doing that? Yeah, because now okay. Sorry, folks. Minor difficulties. Okay. Now we have our initial guesses. Now we can just go straight into our function. Okay. So I'm gonna just go down here, not too far. Um, that's the next part. You don't gotta worry about that right now. Okay. So we would say call our new function new in two. That's our second new function. Um, we still have an I range. But we do want to have our definition. So we want to have our function that we have listed here in the Jacobian. Make sure it's in the Jacobian what is it called? Not area, but Jacobian domain, something like that. I hope I said it in the right reference. But in the Jacobian domain, what we want to do, we want to have our f. So we will say this f of Jacobian basically equal to Jack's Jacobian of our f of our function for our root solver. Okay. So now we have here, we can go back to our for loop. So our for I range and max integer. Let's say our x2, which is right. X2 is equal to x1. Yep. Minus, and now this will also be different. This will be JMP dot linear algebra dot what is it? Let me see if I remember. Dot inverse, yes. So this is the Jackson-Jacobian inverse. And this is yeah, Jackson-Jacobian inverse of our function, and it's being the x1 region, which is correct. All right. And then divided by, there's no derivative anymore. We just have our function. So f2 of our x1. Me, yeah, of our x1. I may do x1 and x2 since that's why I think I shouldn't have done an x2 here, but I needed to define both variables. Hmm, because this is not right then. Um, when we do print both of these out, we print them out. This is correct. And then for our if statement, the only big difference is that now say that the instead of our MP absolute, we need to put it in the Jacobian domain. So it needs to be J MP dot, of course, I mean again, linear algebra of the norm. So if this is less than our tolerance, which our tolerance is still 1e to negative 14, then we need to break. And then our x1 will still be equal to our x2, and we'll still print these out. Okay, so if we shift enter, this should work. Oh wow, I was actually not expecting that to work. Newton, well, if this works, I'll be shocked. I'm not gonna lie, I thought I'd get this wrong. Let's try it out. Our Newton of F2, comma, and then let's just do 2.8 again. Yeah, I knew this was kind of messed up. Okay, so Newton 2. Mm, I still don't like this top part being like this. I don't know if it should be x1, x2. It makes sense, but I don't know if that's right, because then this may not be right as well. So we may have to define x1 and x2 as well, which that is incorrect. Hmm. Actually, no, because our big function is defining correctly. Our two functions are x1 and our x2. In this case, is they're both x1s, but um. Oh, sorry. It's supposed to be our initial guesses, so it should be x naught. Shift enter. Okay. Well, that's still not right. Okay. Argument to inverse must have a shape. Where's that at? Yep. It's this bad boy right here. I think it's this. Let's see if I just put x2, what would that do? Yeah, it's something to do with this. I know this is the problem here. I'm gonna be right back. I'm gonna check what the problem is. I think it has to do with I think it has to both do with our big F that we have for our simple problem, or we plotted both of these out because I'm not sure. I don't think you need to find both our x1 and x2, but that does make sense. I mean, you need to find that because it's written in our problem statement. And I also think it has to deal with our x when we define our equation for x2 due to our f2. I think everything else is correct though. I'll be right back. I will see what the problem is. So my initial statements were correct. It was due to our initial value, and then this line right here. So for our when we define both of our functions and say that as F2, I was correct at first that we just have to utilize X for the position, nothing else. But when we define these, what we will do is that we will use the placements of zeros and ones. So this would be our initial. So when X is at its first number, we will plot this out, and then we will do that for all of our x1s in this case. And for our x2s, we would just put state 1. But yeah, we will represent this like x at position 1. Like it actually is x at position 1, x at position 0, x at position 9. But we have to represent it like that as well. Okay. So now this should be fine. Why is it still saying the flow thing though? Does this also need to be in a column? Maybe. This may also need to be in a column. Let me do something. JMP.array. I'll just make it into array. Um, Maybe that would help. Maybe that is the problem actually. I'll do this. Okay. I don't think this is necessary. I think this is fine though. And then we have to fix this. So the JMP linear algebra, when we do the inverse of Jacobian, is correct, but we need to define this first into our function as a Jacobian. So we have to implement the f jab, and then this will be at x1. So this is correct. And lastly, we have to do our matrix multiplication. I forgot to do matrix multiplication, not divide, of our f2. And of course, this will be at x now. Okay, so now we have that. This should work, hopefully. Flow object is not callable. What do you mean? Let me put this back up here. What do you mean by flow object is not callable? Why is that the case? Why is this not callable? It's the second part of our function that's saying it's not callable. Yeah. Let me check again. Should be the last time I check, and then we can figure this out. So it definitely has to deal with this again. I know this is correct. Oh, this needs to be X1. I'm sorry. Yeah, it has to do with our initial defining our two functions. So it'll be the last time I come back and we can finally get this figured, squared up and figured out. Okay. Okay. So I checked it out. It's something really small. I should have caught this. One, for our array, we need to put this in parentheses. And secondly, on the point five, I forgot to multiply it. So yeah, that was it. That's why we get rid of the yeah, that's why I kept getting errors. I kept forgetting to multiply the point five. Um, but yeah, everything else works out. Um, Bada bing, bada boom. We get our answer. So what you see here for the newtons, for our root solver for newtons two, for our nonlinear multi-function system. Um, you see that we have two brackets, two columns. One for the first function, one for the second function, and they're just based on our initial guesses. Um, as you see, they both take around six in six rotations. So six the root cell run six times for them to find their what's the word for it? Their the root. Oh my gosh, my mind just blanked. Oh my gosh, to find the root. So as you see, for our function two, we actually were able to find the root. Um, you see here, we get a 0 and a -5. Well, we get at root 0. So we say one of our roots is 0, and it goes to negative 5.5 e to -17, which that's 0. That's 0. That's 0. As close to that's 0. Okay. If it goes to the -17th digit, that's 0. So we were able to find a root for one of our functions, but we were not able to find a root for the second function. So for this, you kind of see that we're not really able to find the roots of both functions. We're kind of able to only find the root at one of the functions we have. Um, Let me see if I switch to, I mean, I know it just depends on the equation. Yeah. So even when we like switch stuff around, we make some bigger, make our initial guesses bigger. Um, I'm pretty sure we're only gonna find, we're not able to really find both of the roots. Because it will break out once one of the roots for either of the functions will stop. But we are able to tell what function, what roots are for which function. So we can kind of play around with our initial guesses and then try to find the rest of the roots for our function two, or to start finding the roots for our function one. But yeah, that is, let me move this over here again. That is um the implementation of a nonlinear equation using Josh Jacobi, implementing the Newton's Raster method. So we kind of got all three of it done. The rest we have is the Thomas algorithm method, which is way more complicated than what we are this learning. So it's not too bad. It's kind of similar to what we learned earlier in the semester. I forgot what we did, but when we kind of started introducing matrices, and we had, what was that? I'm trying to think what it was. We had five, it was into. Oh, it was the heated bar. Yes. So when we had our heated bar that we had a hot plate on both sides. You remember that situation we had? I think it was like 2 videos ago. But yes, when we had to do the matrices we had to do matrix multiplication of a large like of different multiple positions. It kind of works out like that. Um so we will get into that next and we will work that out. Okay, continuing on with our part A, we are now going on to the Thomas deriving and explaining the Thomas algorithm for solving tridiagonal matrices. So, the purpose of, let me put this to the bottom. The purpose of a Thomas algorithm is kind of what like it says here, is it basically to solve for linear systems that have a tridiagonal matrices. So for example, hopefully this, I wish Wikipedia was more in detail, but I know it's not. But I can explain it. But basically, like if we have a system, kind of like when we had our linear, and kind of we set up like our when we in the previous video before we did our linear heated rod, which had heated plates on both sides, and we had a matrices, a diagonal matrices. And basically. What the purpose is of this is kind of finding, instead of us trying to find our n, so like in our heated value case, we had a current position that we knew what position we're starting from across the entire heating bar, and we're trying to figure out the temperatures throughout. So we're trying to find our basically our y, our final y in our case. But in this case, for our tridiagonal matrices algorithm, we are trying to find the x. What's it say? So, but I'll explain it more. I'll just go into the derivation, not kind of piece things together, but let's go to the derivation. I'm gonna stop sharing, and we will do this on my iPad. And then, yeah, yeah. So how I said, I'll do a 4x4 matrices. And what color do we want today? Let's do purple. You know, y'all did purple, so let's do purple. So we have a 4x4 matrices. Um, wait, how do this? 4x4 matrices, and we kind of go like we can start with what? B1, C1, 0, 0. Let me erase the bottom part actually. We have 0, A2, B2, C2, 0, 0, A2, B2, not 2, 3, 3, 3, 3. Then we have 0, 0, A4, B4. Okay. Let's say we have four matrices. using the variables A, B, and C. And then this gets multiplied by a certain number of by x's. Okay. And this can represent like our position. Um, so we have a 4 by 4 and a 1 by 4. Okay. And this will equal out to our epsilons. So epsilon 1, epsilon 2, epsilon 3, and epsilon 4. Okay. So here's kind of I was kind of trying to piece together, but if you remember our heated bar, we had our positions. So like this case with this, our A, B, and C will be our positions, and then we'll multiply by the N in this case. So this would be the N if you're referencing our heating bar system. I don't have a reference to pull up. I'm trying to remember off the dome. Um, for number of spaces we're going forward or backwards. So this was the position, and this is this. No, what was it? Trying to remember the example. Okay, let's just scratch example so it get less confusing. But here we have our 4 by 4, 1 by 4, um, bar linear functions, and basically, um, how this will work is, in the general case, if we did row by row, how this will work is that we're trying to find our epsilon one, so it'll kind of go like B1, X1 plus C1 X2 plus 0 is equal to epsilon 1. A2 x1 plus B2 x2 plus C2 x3 plus 0 is equal to epsilon 2. Um, 0 plus A3 x2 plus B3 x3 plus C3 x4. And then 0 plus 0 plus A4 x3 plus B4 x4 is equal to our epsilon 4, arrow 4. Okay. Here's how the case would kind of work out. This is how it kind of multiply by. If we do row by row, this is how it will look like. So this is like if we wanted to find our epsilons, this is how it look like. Before this case, or actually doing something a little bit different. So we will use this, but this is kind of not how we would well, this is this is how it would generally be set up. But what we would kind of do differently here is that we will modify our C values and our epsilon values. Okay. So we scroll over. I'll change to orange. So go over here. Kind of like I mentioned. If we reset this up, because in this case we're trying to find for our epsilon, but in the alternate case we're trying to find our x's here, what will we do? Well, what we will do, basically, how this kind of work out is that our B cases, as you see here, our B's are the longest diagonals, which has 4. So our B's would be equal to the number or actual number 4 our matrices, and our A values and our C values would be n minus 1. Okay, I just want to make that note because we have to do mention that later on. But if we go to try to find the other side, we're trying to find x. We would basically note that our B diagonal would kind of equal out to 1. So they'll all be ones. It'd be 0, 0, 0, 0. Oh no, this would be 1. Be 1, 0, 0, 1, 0, 1. And our C values would be C star. Maybe 0, 0, C star. Let's be 1, 2. PC3 star. Okay. And the reason why we have a star, because this represents our modified. So what we're doing here is that we will modify our C's to kind of rework out the matrices to find our X's. Because in this case here, our X's will still multiply by our 4 by 4 matrix C, but the X's will remain the same. They don't get modified. And then our epsilons will all be modified. Okay. So basically what we will do is that we'll use of course we're generate the use the same. Let me kind of re say this. So basically what we're doing is that we are trying to find our X values, okay, using our tri-diagonal matrices that we have. In our original case, if we were just trying to find our epsilons, we would just work out the way in the purple that we would just we would do a matrix multiplication of both the 4 by 4 matrix C and the 1 by 4 matrix C of the ABC times the X's, like I represented down here to find our epsilons, which you see in the cases right here, okay? But in the case that we're trying to find our X's, kind of rework it. So basically, we already have our epsilon values. Basically, we already kind of have our epsilon values, and we have our epsilon values. And we have to rework our 4 by 4 because in our 4 by 4, if you remember, in our back to our heated bars equation, the heated bar situation, the B's kind of went out to 1. So kind of like our B's here, the longest diagonal went out to 1, like you see here, and our C's will go to 0. Will be modified based off of that. Okay, so by having our C modified, our epsilon values will also be modified as well. So due to our C values being modified, our epsilon values will be modified, resulting in, what is that should makes it, well, that's the reason why. Um, I think I'm explaining this really, really wonky, but basically, for this to find our X's, we have to modify our C values and our epsilon values to then rework back to find our X's that we're trying to find. Okay. So now let's try to find our X values. Okay. Let's use green. So X values. So we can start with the first column. So it should be this bad boy right here. So what it is, all it is, we have B1 plus C1 plus 0 plus 0 will give us our epsilon 1. Okay. Now it's kind of like there's a few steps you take, and it's kind of like a same step. So it's kind of it gets pretty simple the more you kind of understand what's happening. It's kind of like it's a cycle for what you do each step. But the first step you do after we introduce our first row, um, is that we divide by our B1. So okay, so we go back to green. So we divide by our B1. That will leave us with 1 plus C1 over B1 plus 0 plus 0 is equal to epsilon 1 over B1. Okay. Now from here, you kind of see kind of what I'm kind of talking about. So for our first value, now we have our 1, which represents the one we have here for our row. We have our first modified value for our C's, which goes up here. And then we have a modded epsilon value here, and our epsilon 1 divided by B1, okay, which represents up here, okay? So then, so this is how we would basically start off our first row, and then we would go to our second row. So what we do next Is that step two? We will, what is it? Subtract. No, we will multiply by A of the next integer. So basically we're multiplied by the next row of A. So it'll be for the next case, it'll be A2. So I in this case would be, we can do IN, I mean AN. We're basically multiplying by the next series of A. Okay. So next step will give us multiply 1 by A of it'll be A2 now. So A2 plus A2 times C1 over C divided by B1. So it'll be A2 C1 divided by B1 plus 0 plus 0. Okay. And this would be equal to A2 of epsilon 1 divided by B1. All right. All right. Next step, I'm going to use this one. Next step, step 3, is that we will introduce our next row. Okay. So this will be, we'll now bring in, I'm gonna label these two so we know which row we're working with. So now this would be our second row. So this would be the A2, B2, C2, 0. So now we have A2 plus C2 plus B2 plus C2 plus 0 is equal to epsilon 2. Okay. And then next, we will actually subtract. You will subtract our step above, so this step here with our second column. So we'll subtract step 4 minus 3. So we'll do a subtraction here. This would be it'll be a second row divided by the multiplied A2 row, and this will give us, so we have A2 minus A2 is 0, and we have plus, so we have B2 minus A2 of C1 over B1. Then we have plus C2 minus 0, which is a C2. And then we have 0 plus 0, which is just 0. Okay. And then this would be equal to epsilon 2 minus A2 of epsilon 1 over B1. All right. So now here, you kind of get the gist of what we're doing now. So basically what we're doing is that we're taking our initial rows that we have from our original 4x4 matrix C, and like I said, we're modifying. So we're modifying our rows to kind of equivalent to what we have for our next modified version. So, oh, I'm not done yet, but our next step is now we'll go back into the cycle, and then we'll divide. Step 5, we would divide by our B term, our B2 term. Okay. So in this case, we divide by B2 minus A2 divided by C1. We'll do B2 minus A2 divided by C1 times C1 divided by B1. And this will give us 0 plus now 1, because we're dividing by this here, plus 1 plus a wacky number of C2 divided by B2 minus A2 times C1 divided by B1 plus 0 is equal to this big form of E2 minus A2 epsilon 1 of B1 divided by B2 minus A2 of C1 of B1. Okay. So now here we have, let's kind of scroll it up a little bit. We have our matching 1 for this row. We have our new modified value for our C right here. Then we have a new epsilon. Okay. And then we'll keep doing this for each step. So for row 3, we will start by going from the top of the row here. So we'll multiply by the next A. So we'll multiply that by next number for A. So it'll be A3 times this row. Okay, we'll introduce the next row. So it'll be this row will be the next one. Then we'll divide by the B term. We'll introduce it, we'll subtract from the previous step, and then we'll divide from our new B term, and then that will give us our new 1 C3 modified, and then our epsilon 3 modified. Okay. So you kind of see it's kind of like a cycle, and you can kind of get that this can get kind of crazy once if we have a big matrix C. So if we do have like a 10 by 10 matrix C with x of 10, then that matrix gets multiplied from x of 10, which equals to epsilon from 1 to 10. This could be the derivation could get kind of wacky. Okay. But here's basically kind of how it is. We can keep going for epsilon 3, but it is going to get extremely big. This is kind of the basis of it. And I actually have it up on my sheet for when we do the derivation, so I can kind of show you guys what the third row look like. I didn't do the fourth row, but from the fourth row, we do know that x4 at the last x value is equal to our last epsilon, our modified epsilon value. So we know from this, once we do all the modified and derivations, we know that our last epsilon that we do get is actually equal to our last x value. And this is actually very important because this will help us in our derivation. Because basically what we will do in the Python is that we will kind of hard code out all these derivations inside of Python to basically get this worked out. And we are kind of from this, since we know that x4 and epsilon 4 are equal to each other, we will use the x4 and basically rework everything backwards. Okay. So they basically do the derivation backwards to get our x1s, if that kind of makes sense. And it'll make more sense in the Python. But here's kind of the derivation. That's kind of the most simplistic way I can make it of the derivation. And then we will get to the Python code next. Okay. Okay, so now after we just derive the Thomas algorithm, let's now put this in the Python. Okay, let's code this up. All right. So I actually already have code ready for us. This is for something later in our code, but should enter for our first line. I'm gonna actually just move this. Oh no, move this down here. For our libraries, we just do NumPy. So we're just importing NumPy. So import NumPy as NP. Okay. Enter. Okay. Next we'll do random. So you want to import random numbers. And I'm gonna actually put what Jay said, which is kind of like if you ever play Minecraft and you spawn, you get a random seed. And this is kind of like this is basically acts like your seed. So basically, we will be generating random numbers for our matrices that we're doing. Um, By using having actual number for our seed for our random state, it would actually give us it would allow us to always keep all random numbers so it doesn't keep generating new numbers every time we shift enter the coding in. So that's basically what it is. And we'll call this R&D better. So now let's start with our diagonals. Okay. So we will be working on this bad boy right here. Oh, and here is also, because I know I didn't mention this, it's kind of the rest of it. I went to three. I didn't go to the fourth one as well, like I said, but I went to three using the same set, so multiply. So we were here in our derivation on the iPad, but all I did next was, of course, multiply by the next A, multiply by A3. So we did A3 here. Then I introduced our third row. So the third row for this column was a 0, A3, B3, C3. Introduced that with our epsilon 3. Subtracted our step 7 from our step 8. So we just subtracted the step above. We got a 0 plus 0 plus B3 minus A3, C2. This is a lot. C2 divided by B2 minus A2 times C1 divided by B1 plus C3 is equal out to the epsilon 3. And then I'm just going to say to the modified to the no, it's not even modified yet, but yeah, to this subtracted by our previous epsilon 2. So there. And then we divided by our B term again. So we divide by our B3 term, which is this bad boy. So everything gets divided by that. And then we will, for four terms, do the same thing. But yeah. Yeah, I didn't want to write all that down. But this would be to our third term and our fourth term. We'll keep going. So yeah. This kind of looks like, I know it gets, like I said, wonky. But yeah. So let's start off getting our four by, actually we're doing five. I forgot to say, yeah, we're doing five. So n is equal to five here. So in the example we did in class, we did five major, we did 5 by 5. So I'll just use five for matrices. Yeah. So what we would do is that for this our diagonal, we will use something called numpy diag. So it basically help us create these diagonal matrices. So if we want to just have a diagonal for, let's go back here, for our B line, we can actually just make a diagonal, have a diagonal just for the numbers in the middle and everything else will be zeros out, which is kind of nice and convenient. So if you want only diagonals for our A, which is our A terms, our B terms, and our C terms, we only need to do three NP diagonals for our matrix C. So what this will look like is that we'll do first we just do the random. So we do what is it? R&D dot random integers from 0 to 10. The size will be n. So we'll do our B term first. Our size will be n. And what else? I need the K term. Oh no. So this works for our random. So our size will be n. This will represent RB. Let me do this is B RB. And then we will need to add in our random integer. I mean, so we need to add in our numpy diagonal. So np dot diag. And then this will be um so we have to import K as well. So K is a diagonal in question that defaults that defaults to 0. So basically is where you want to start your positioning for your diagonal. In this case it will be 0. So we start at I keep messing up at 0 here, which of course in code 0 is our first value. So we start at 0. It kind of shifts over by one column every time you increase K. So we'll do K is equal to 0 here. Okay. And this will be our first diagonal we have here. Next we will do we can do the C. column. So same thing here. I can actually just copy and paste everything. And, but this time it'll be -1 because we only need four terms because our kind of like we said here, our C and B, C and A's are n -1 and our N's and our B's are n. Okay. So it's be -1. And then this C will be in the next position over. So our K will be 1 here. And then we will add again and then copy and paste. Oh no, I messed up. I messed copy and paste. And this should just be -1 now for our 1. I'm gonna just move this. Actually, you can see now. Okay, -1. Okay. And this will just be equal out to, so if we shift enter this, what's the problem? MP diag. Oh, I meant 1. There we go. Let's run all this again. Why is that the okay? Because I did this earlier, and I know that's not correct. So what did we mess up here? What did we mess up on? I think it looks right. I actually don't know. This should be right. Actually, yeah, this should be exactly what we need. We have our random numbers from 0 to 10. For our B column, we have for let's copy and paste this. I think it may be this one. It should be yeah for this column. That's correct. Oh, is it our seed? Maybe our seed. Because this one does so that captured our A's. This captured our C's, yeah. And then does this capture our B's? Yeah, capture our B's. Interesting. Um, let's say because in our thing we also I'll name this as A for this case. Maybe that will work. I don't know. This should work. Um, it's even worse. Runoff. It probably is my seed then. Let me make sure I have the right seed, and I'll be right back. Okay, so small mistake. We had it from 1 to 10, not 0 to 10. That's the reason why. Um, it did not go as I thought. Let me run this all again. There we go. Yeah, that's the correct one. I know it's 7.5 is right on the top and 1.7 is right on the bottom. Okay. So yeah, here is our basically our matrices to start off with. And we also need epsilon as well captured. So we'll do the same thing for epsilon, which we represent as E. This is equal to, and we can just copy and paste as well. Oh, not our seed. Copy and paste as well. 1 to 10. We don't need the K. I actually don't need a diagonal. Yeah. And then E, or yep, and that's right. Yeah, and that's the correct D. Yeah, we don't need diagonal because it's not diagonal, it's just a vertical column. So you don't need diagonal for this case. But yeah, here's our A. So our A is basically representing our matrix here. Actually, I represent this as M for matrix. M for matrix. Then our E for epsilon. Okay. So there's actually a way. So in Python, there's actually a way we can actually do our tridiagonal solver for x's already. All it is np dot linear algebra dot solve for m and then for e. If we do this, let me show everything here. We do this. This is actually all of our x's from top to bottom. Yeah. It actually already does this for us. There's already a solver in Python that already does this kind of this Thomas algorithm equation. But what we want to do is we want to do it ourselves. So we don't want to use Python. We're saying screw Python. Let's do this ourselves. Okay. So this would be our reference though. So at the end, we will check to make sure that all of our solver is correct. Our manual solver is correct compared to the Python solver. So we know this is correct. We want to make sure ours is also correct. Okay. But yeah, this is just just want to let you guys know that this is already a thing. We're not. It's already in Python. So we're just doing the hard part. It's already one in there if you ever need to use this. Okay. So let's start. Okay. Let's start. So first, of course, we already know that in our modified region, we know that our C's and our epsilons, not epsilons, but our E's get modified. Okay. So we need to actually write this down. So we need a C mod, E mod, okay. And all we can do, we only need is we can do NP dot zeros, NP dot zeros. For both of these, oh, for for C's it is for n minus one. Because it's four of them, and then for E it's just n. Okay. We'll be using these, putting information in these later. We can just say zeros for now, just for a filler. Okay. So first, for our first moderation, we want to first capture our first row. So we want to capture first our C1 and our E1 in this case. So how we can do that is C mod, E mod, and this would be at position 0. Okay, position 0. And we know that in this case it should be we know that our epsilon B1 is just E minus B1, which if we do that, let's represent well, let's do at the bottom, right, M and then E. Okay, run all. Yeah. So we know for our C modified for our first row, we know that it's C1 divided by B1, which in that case we know that our C1 would be what? It would be 5 divided by 7. So 5 divided by 7. And then for our E, we know it's E1 divided by B1 for our modified E, which we know that is just 4 divided by 7. So we know that's just 4 divided by 7. So we do this. This is our desire. This is our numbers we're trying to look for. Okay, so if we use what we have up here for our matrices, we know this we would just get M 0, comma 0, which means our first column, our first row and our first column, which that is our B. You want to do divided by, and this should be M, same matrices, but of 0, so our first column, and then the second, our first row and the second column. Okay. So this will be our our first modified C, and then for our E, all we'll do is our first position of the E divided by M at our first column, first row and the first column. Okay, let's be a copy one. We shift enter and we print out C mod at 0 and then E mod at 0 as well. Oh, I forgot to do. We get our desired values. Perfect. Okay. So yeah. So now we have captured our first row here. Okay. Next we want to capture now is our rows 2 through 4. Okay. Um, which we know. So we can do a for loop for this because it runs for 3 iterations. So we'll do for I in range of we want to start with 1. So for a 1, because we know we start with the first our second column, the second row, and you know in Python, 0 is our first position. So it'll be 0, 1, 2, 3, 4 is all the rows in this case. So we want to start with our first row in the Python, second row in real life. We want to make this all the way to our fourth row. Okay. So that would just be n minus 1. Okay. All right. Um, so we know in all these rows, the reason why we separated our initial, our middle, and our last, because for our initial row, we only have our B and C term. So we only need to really find our B and C term in this case. For our second through fourth row, we have A, B, and C represented in the matrix. So we need to capture that as well, separately, because it goes through. It needs to go through a for loop because it runs 3 times. I mean, it doesn't run 3 times, but it has all the 3 variables in the matrices. So we need to kind of separate that out before we combine them together. And then of course, the last one we'll do the same thing, kind of separate it out, kind of like this. So. Well, we'll be using A and B instead of B and C. Okay. So now for this, like I said, we have all the variables. So it'll be A, B, and C, and this is equal to what is it? I forgot what it's equal to. Shoot, this is on the blank right now. I can kind of skip this stuff for now. We know that we have in this case we have 3 factors. We have our B modified, our C modified, and our E modified. And we will start with kind of like our second column here. So, because we know for our second column, our second, we'll start from second column, and these would kind of run the same way. Um, so we can just represent a second one, and it will go through the for loop 3 times, so it'll work. Let me actually make sure this is the right. So print I and make this all. I don't know how you do this. How does this print I 1, 2, 3. Oh, I need to make it longer. Because you have 0. Oh, no, that's right. Yeah, 1, 2, 3. Yeah, we have 1, 2, 3. Perfect. Okay. So, all right. After this, so B mod. Um, so for our B mod, what would it be? Well, I know for our C mod, this would be what would it be? Our C mod, we will have. Oh, I'm blanking right now. So we do our second column. We know that this would be this. So that would be our M at. Oh yeah, we use I. That's why. So we use I in this case is 1. So it'll be at I, comma, what is it? 1. So it'll be I in this case is 1. So it'd be at 1. And the C is at the third position. So it'll be at what? Not here. So plus 1. I plus 1. Okay. Divided by, yep. Divided by M. So we divide by B2. So B2 in this case is at I, okay, minus A2, which is M at I minus 1, um, times our C1, which is our C mod that we already have. Because we know our C mod is already our C1 divided by B1. So we can just say our C mod at, does it be I in this case? Well, I is at 1. So it'll be I minus 1 at our initial position. Yeah, so I minus 1. Okay. And our E would just be, um, we have that here as well. It'll be this bad boy right here. So it'll be this. So it'll be E2. So E at I plus 1. I plus 1 minus, oh no, it should be E at I minus A2. So you know A2 is M of I and I minus 1 um times our E mod. It's like our C mod is E mod, is already represented like that. So E mod of I minus 1 and then divided by, and then it'd be divided by this right here that we already have captured. So copy and paste. Okay. Okay. And then our B mod is just 1. So yeah, we can just have to, we all you have to say is that our B mod is just I. So can I just say that? No. I know that's wrong. That's definitely wrong. Um, oh, I remember. Okay, so A, B, and C. Okay, it just hit me. So A, B, and C basically represents our 715 here, 935, and 561. So we have to capture all these three columns in our A, B, C's. So what we will do, and I just clicked. Thank goodness I clicked. Okay, so we do M of I, so our first column to I minus 1. So it's to our, what is it? So we have our first row, and it stops at our last column. No, you want it for, it'd be minus 2, because we want it to stop at, so we have I minus 2. So we have 4, 3, 4, 3. So our last term, we want it to be 3. Okay, which, oh no, our I only goes to 4, only goes to 3. So yeah, we wanted to stop at 3. So minus 1. And then we have M of I to what? Is it I to what? Well, that's at what? You want to be at the last term. So this is what? 0, 1, 2, 3, 4. I goes from 1. So it already starts at 1. Oh, wait, let's talk about the columns. Yeah, let's only talk about the columns. So it needs to be from 1 to that, from 1 plus 1 to and the range should end from, hopefully this is right. From, should it be at I minus 1? Trying to think here. Trying to think here. So we have I. Trying to think. I'm trying to make. So we have I minus one. I minus one would be two. Let me just see what A and B are right now. So should enter this. This should be fine. Unexpected ended. You don't know. Okay, we can just copy and paste this again. Oh my gosh. We'll figure this out all out later. Shift enter. All right. Okay. And then reprint out. You get seven. All right. Rerun everything. 799. What the heck is that coming from? 955. All right, this is all wrong. Okay. I'll be back and figure this part out, and then we can continue. Okay. Okay, so took a while to actually figure out all I need to do. Because it was actually a lot of mistakes I made with this. So it all deals with our for loop, of course. So to start off, we actually don't need all of this to describe all of our A, B, and C's. All we need to do actually is from this point on, just do an I plus two, and it captures all of all the, oh my gosh, what's happening? Sorry, what's it? I don't know, it was something weird. But it captures all the A, B's, and C's for all the three looping rows that we're working with. So we should enter this. We didn't get our rows that we were actually looking for. So perfect. So now from here, we actually so how we work this out is excuse me, from our B mod, and I have it over here because I was doing practices. Let me put it back over here. Um, so for our B mod, modified B, we would just actually be writing what is it? We'll be retyping out this for portion. So our B minus A2 times our C1 of C1 divided by B1. So what that would be like, it will be B minus A times our C mod of I minus 1. Okay. So that's our representation of our B mod, which is our B and A that we're pulling from our for loop that we have from here. And then times our C mod that we have up here. Okay. Next we have our C mods, which our C mod is actually way simpler than I thought it would need to be. So our C mod is really just our what we have up here is just C divided by B, but it's C divided by B of all the terms we have in our for loop that we're pulling from our matrix C's. So all we need to do is C divided by B. And then for our E mod, um, I started off right with the E of I. So it is our E of I. So it's our E of the epsilon we're working with. But all we have to do is we have to just do subtracted by our A times our E mod of our previous loop. Since we're also pulling the same thing that we did from up here. So this is all we actually have to do. I made it way more complicated than it had to be. But yeah, this is all we have to do for our rows, our second, third, and fourth row of our matrix C. And so now we can go to our last row I talked about earlier, and we can actually just use all the information we did for the in-between rows. But the one thing we can actually change is that we don't need our C because he's not in our last modification, in our last row. The only variables are A and B, so we only need A and B. So we can take our C out of this. And since we're not in a range, we can't do this method anymore. We also need to incorporate our ends because our end is now our counting our variables, not i's, because again, we're not in a range. So we need to do I for the last row, so n minus one. And then for the second to last integer in the row, so n minus two, that represents our A. And for our B, it'd be kind of the same thing, but is now our last is just, it should be minus one. So it's pulling the last integer from the last row. Okay. All right. And then for our B mod, it kind of stays the same. Um, this just stays n, and this is pulling the C mod for our last. Yeah, it should be, what is it? Yeah, that should be correct. And then this should just be the last value for our E of pulling the last value. So our 8 from our E that we have from our original. And then minus our A, I mean, oh my gosh, I can't talk. So we have our E matrix minus our A times our E mod of I minus 1, which it should be N, and it should be pulling our last one, N minus 1. So yes, that's correct. Okay. This should be good now. I think all we actually have to do for our E mod, we could just say -1, and that works as well. But yeah, is it -1 or -2? Should be pulling the previous, so it should be -2. Okay. Yeah, that should be good now. Invalid index. Oh, also I forgot to divide by B mod. Oh my gosh. The good thing I caught that. So I gotta do this same thing for here too. I gotta divide by our B mod, which it shows here. Remember, the bottom portion has to be divided by our modified B. So yeah. And you also do the same thing here as well. B mod. And this will be for I's for the integers because it's our B mod, it stays the same, but our C mod and our E mod fluctuates from for our range. So we have to do that. Why does it say our invalid index for scalar variable? What's the exact problem? Why is it? Let's, I need to disconnect it. Why is it doing? Oh, now it works. Okay. Index 4 is out of bounds. Hmm. Why do I keep having problems? It should work. How's it out of bounds? Thought I had this. This is not, let me index. What's the problem? Yeah, it should be at the fourth one for our B mod. That should be at the NF4 for, yeah, that's correct. This should be -1. Yeah. Let me check again because this video's getting long. I don't want to keep. Yeah, I'm gonna check real quick. Okay. So I found the error. No, don't mind this. Um, but the error is that we need to. This should actually be to the second, negative to the second. So it's basically saying because I did to the -1, which should be that's pulling the fifth term, but I need to pull. I mean, it's pulling the fourth term. No, what is it? Because right now n is 5, and what is it? We need our matrix Z. N is 5. Oh yeah. Okay, so our matrix goes to 5, but in the matrix it goes to 4. So we need to make it to n-2. Yeah. Okay. Yeah. Okay. That's what the reason why. I don't need this. I was incorrect with this. And this was correct before. Yeah, so should be good now. If we run all, this should work. Yeah. All right, so if now to actually find put in our solver for x, we'll just kind of repeat what we did up here for the zero. So it'll be x is equal to np dot zeros of n, and we have 5n, so I mean 5x, so it'll be n. And of course we know that our last n, so our last x is equal to our last e, last modified e. So it's equal to this value here, which I should actually, there we go. What? Let's run all. There we go. Okay. So now we just need to do a for loop. So for I range of, and this will be I, comma, and we're trying to have it go backwards because now, as I said earlier in the derivation, we know our x4. So from our x4, we then figure our x3, then our x2, and our x1. So we need to go backwards, kind of. So all we have to do is that we do I. I is in range. Oh no, we do n. We do n. So it's for I in range of n. So we know n is 5. And we're going backwards from -1, and then we do -1 again. So that should be our. Let me print this out and make sure this is correct. Shift enter. No, so we need to start at what is it? At 4. So it needs to be n-1. 4, 3, 2, 1. Is it 3, 2? Is it 3, 2, 1, 0? 0, 1, 2, 3, 4. No, we have 4, so it needs to be at 3. So I mean -2. There we go. So that works now. All right. So now all we need to do now is that we need to find our x. So x at I, this is equal to E mod. No, yeah, it's equal to our E mod at I minus our modified C's at respective I, and then times the x of the, what is it? The x of the next next value. Okay. This should work. All right. And we get our x. We can copy paste this. And we copy paste we find our x. This is so off. Let's run it all again. It's so off. What's the problem now? Oh, it's been so long doing this. What's the problem now? Um, I'm gonna check again. Maybe our last pause. We'll fix everything up and we should get our solver working. Okay. I had to catch my mistake. It's just I forgot to put parentheses around the back end here. But now this should work. Shift enter. Oh, what did I do? Oh, okay. Okay. Let's run again. This should work. If I run all again, still doesn't work. Let's just repause it then. Okay. After a while, finally looking over, cause it's late and I'm tired. I figured out my mistake. One, I forgot to put parentheses again. I don't know if it keeps happening. I forgot to put parentheses again around the B mod. And then I forgot to also put B mod for this as well, my modified B. So now with this, I think it may still shoot out a wrong answer, but our numbers look more like what we're getting. Here we go. Here we go. All right. So our solver works. Yes, our solver works. Yeah. So this is our solver for finding our x values. Yeah, yeah, it worked. So here we just compared our the NP not linear algebra solver that already is in Python to our solver that we made using a derivation. Um, and we got the exact numbers. So we can change n to anything we want now, respectfully. And it'll be able to shoot us out new code. And yeah, and we'll be able to find the x's respect to our tridiagonal matrices. So here it is. That is the end of our part A from work 5. We will get to part B then in the next video. Okay. See you later. Oh, yeah, see you later.